Our first presentation here on the main stage showcases Pi2's innovative approach to Universal Verifiable Computing. Please welcome Grigore Rosu, CEO of Pi2, as he shares insights into the proof-of-proof technology and its potential impact on the blockchain landscape. Please welcome Grigore.
All right, thank you. I am Grigore. I am a professor of computer science at UIUC, also the founder and CEO of Runtime Verification and Pi2. And today I'll talk about Pi2, which comes from proof of proof, ZK proof of mathematical proof, which we believe will serve as a foundation for what we call universal verifiable computing. Before I dive into details, I'd like to tell you the main theme of my presentation today, which is that I believe that we are close to having a paradigm shift in verifiable computing, where correctness is paramount and also universality. We call it verifiable computing 2.0. Let me first tell you a few words about verifiable computing 1.0, the current state of the art in verifiable computing, and why we believe we need to do something about it. So first of all, it is a very fragmented space that lacks interoperability. We have lots of different programming languages, lots of different virtual machines, and VM-specific ZK circuits. And all this leads to a huge trust base. There is literally millions of lines of code that we have to blindly trust in order to claim correctness of computation. So to claim correctness, we have to trust millions of lines of code in compilers, in VMs, in ZK circuits. Maintenance is very hard because all these VMs and languages evolve. Any VM language or programming language worth its salt evolves every few months. So we spend a lot of time to implement a ZK VM for a particular VM, and then we got 2 or 3 new versions in the meanwhile. So if we wonder about correctness, then that's a lost cause. We should forget correctness. Nobody can formally verify millions of lines of code, period. That's well known. It's very hard to verify such large systems. What we propose in Verifiable Computing 2.0 is to actually take the several decades of work in formal semantics, which unfortunately is mostly ignored by Verifiable Computing 1.0. So I want to take all this and make it a central piece of Verifiable Computing 2.0, the core of it. In a nutshell, why do we want to have formal semantics? What do formal semantics do for us? Well, simplistically speaking, they allow us to regard computations as mathematical proofs, rigorous mathematical proofs. And now we know how to deal with mathematical proofs. The same way TCP/IP as a data integrity protocol is at the core of the internet and enabled innovation above and below because it assures the data integrity of the internet. The same way we believe that integrity of mathematical proofs should be the centerpiece of Verifiable Computing 2.0, which will enable innovation above and below. Above, programming languages, virtual machines, we can invent them, as many as we need, even domain-specific, application-specific languages. Once we have a formal semantics for them, we have a mathematical definition for the programming language, then that produces a mathematical proof whenever we execute programs, and now we only need to worry about mathematical proofs. We have to check the integrity of the mathematical proofs, and now we check the integrity of the computation without having to worry at all about implementing a ZK circuit or any complicated artifact for that particular programming language or VM. And at the same time, underneath the proof-checking integrity, we can have all the universe of ZK circuits and ZK VMs around. You don't have to implement a ZK circuit specific to a particular VM or a particular programming language. We implement it for mathematics. So that's the vision, and we believe that we enable Verifiable Computing 2.0. This is not only a dream. We started working on this about 3 years ago. Well, we've been working for more than 20 years on programming language semantics. but the connection with ZK is relatively new, only 2-3 years. So let's look at this picture. Look at the top where we have the crossed arrows, ZK proof of math proof, right? So imagine a vertical bar to the middle, and now look at the left where we have programming language semantic, the programming language semantics world, and to the right where we have the ZK circuitry world. To the left, we use programming language frameworks like the K framework, which takes a programming language as input and gives you tools for that programming language, in particular interpreters for that programming language, that produce mathematical proofs in addition to the results. So they are like any other interpreter. You can execute programs with a semantics-driven, semantics-generated interpreter. Works exactly like any interpreter. It's even faster than many handwritten interpreters, but not only gives you a result, but also it gives you a mathematical proof why that result is correct. And when I say mathematical proof, I mean traditional mathematical proof, step by step, like we learned in school, not a cryptographic proof. A mathematical proof why that result is correct according to the mathematical definition of the programming language. You see what I'm getting to? This is what we mean by correctness, correct by construction. There is nothing to formally verify here. I just have to verify the mathematical proof, which is done now in the second stage with ZK circuits. Okay, so before we even go into ZK, notice that there are many implementations of proof checkers, mathematical proof checkers. And the beauty of detailed mathematical proofs is that they are very easy to verify with very simple mathematical proofs, mathematical proof checkers. Just to give you an idea, the smallest proof checker that we have for these mathematical proofs produced by the K framework in this case, the smallest of them has only 200 lines of code. Okay, so 200 lines of code, which of course, public code, that you can use to verify any mathematical proof of any program in any programming language. That's the trust base, from millions of lines of code to 200 lines of code. Okay? Now the next step is to implement these 200 lines of code, this proof checker, using ZK technology. All right? And if we do that, then what we get is the same result in the verifiable computing 1.0, namely you, oops, what? So you haven't seen the slides for all this time? All right, we need some help here. Can somebody connect the slides?
They're on the outside screens.
Oh, I see, not on this one. Okay, that works for me. Better. But this doesn't work. Oh, it does. All right. Good, so what I wanted to say is that what we get in the end, now I get it why nobody looked at me and you guys looked on the sides. So what we get is the same final result as in verifiable computing 1.0. You start with a program, you start with a program in some programming language, you execute it, and you get a ZK proof in the end. But that ZK proof now is a proof of a mathematical proof of the claim that has been made. So it serves the same purpose. It still justifies the correctness, a test for the correctness of the claim, but using the same pipeline for all programming languages. You see, there is nothing specific to EVM or RISC-V or WASM or Python or JavaScript or any language here. Right? So that is the big picture and our current implementation of it. And now let's go into the implementation. But first, let me say a few words about the baseline. So what we've done was to start with some programs in two domains where we believe Pi² will have an impact in the future, blockchain and AI ML. So we took two programs of each, an ERC20 transfer program and a batch transfer where we use the same program, we run it 5,000 times to do 5,000 transactions. And from AI ML, we took two very simple models, the perceptron and an SVM model, and we implemented all this in the existing, the major existing ZK VMs. And I would like to express right here, right now, my gratitude to the teams of RISC-0, ZK-LLVM, LERG, and Cairo. They were extremely helpful. Once we explained them what we want to do, they were very enthusiastic, and they said, let's do it, let's implement the best possible proof checker using our ZKVM. So these are the numbers that we got. These are 1 month old. I'm sure now they are better. And I'm sure if they implemented this for us, they will be even better. But just to get a baseline, they are currently between, as you can see, between 0.6 seconds and 2-3 seconds. The batch transfer is a bit heavier, but overall we are in the seconds range. Okay, that's where. So what happens here? We took these programs written in a high-level language, Python or Rust, then we compiled into the ZKVMs, and then we ran them with the ZKVMs and got the ZK proofs. Okay, so that's how we got these numbers. And again, it's just a table with numbers, but this took months of work of lots of people to make them work and get the best possible results. All right, so nothing specific to Pi² yet. There's just the baseline, what you expect in the best possible scenario. If you implement the proof checker using the existing ZKVMs, right? So the next step is to implement the right side of this picture, the 200 lines of code proof checker, in the existing ZKVMs to see what we get. All right, so now we can use ZKVMs, existing ZKVMs, to verify computation in any programming language without a compiler in between necessarily. Okay? So this is what we've got. Initially, we started about 6 months ago. Initially, complete disappointment. We couldn't terminate any proof because our mathematical proofs were horrible, huge, unstructured. We just got something and then we expected magic from the ZKVMs. So then we sat down and said, okay, it's time to rethink proof engineering. We have to generate better mathematical proofs. And the beauty of mathematics is that you can always engineer mathematical proofs, make them smaller, more structured. And we did all that algorithmically, not by hand. So by the end of, in a couple of weeks, we managed to finally get some numbers, like half an hour. It was like a big success. Then 1 month later, after a bit more proof engineering, mathematical proof engineering, we got to the order of, we made it twice faster, but still far, right, from the existing approaches. And that's not unexpected because now you have 2 levels of indirection, right? You have an interpreter of an interpreter in some sense going on. So then we decided to change everything, to start optimizing a little bit, not too much, and we got to much better numbers, almost an order of magnitude faster, and now with the GPU, it gets pretty reasonable, right, within less than a minute. And again, this is just a few months of work using the existing ZK technology to implement the proof checker. And again, I'd like to express my kudos to all the ZK VM teams who are very helpful in this process. All right, no interesting optimizations or improvements so far, just a plain mathematical proof verified with a plain ZK VM. What else can we do to make it faster? Right, because speed is the problem, the big elephant in the room, performance. How can we make it faster? So here are 3 optimizations that we are currently working on. The first one and the most obvious one is let's implement a direct circuit for the proof checker, right? Because the ZK VMs pay a price. They are general. They work with all possible programs. But we need only one program here, the proof checker, right? And we have some experiments, and we get an order of magnitude performance only there. Okay? Then mathematical proofs have an interesting property, different from programs, which is that the mathematical proof is correct if and only if every single step in the mathematical proof is correct, obviously. But what is nice about it is that you can verify every single step completely independently and in parallel with all the other steps. And we are not exploiting that thing at all currently. So the next step is to make it even more parallel. And finally, there are conventional proof search techniques where we can do symbolic execution of basic blocks and compress the semantics of large portions of the program into just one step. It's like having a big mathematical proof and compressing it into lemmas and using lemmas to do proofs, and then you get much smaller proofs, actually. And we did experiments that will bring another 1 or 2 orders of magnitude in performance. So we expect at least 3 orders of magnitude increase in performance over the next few months, hopefully. And finally, And most importantly, I think, for verifiable computing 2.0, is that formal verification, which we are very scared of, but formal verification will be the ultimate optimization that will make things faster, a lot faster. Okay, why? Because when you formally verify a program, you eliminate the necessity for iterations, for loops. Okay, so now you get mathematical proofs which are linear in the size of the program as opposed to linear in the size of the execution of the program. Okay, and this basically makes performance, sky is the limit now. You can make it really fast if you formally verify the program. So developers will be incentivized to formally verify their program. Like this function in Uniswap, we formally verified Uniswap, actually runtime verification. But once you formally verify this, you can use that to make ZK proving even faster. All right, and with that, let me dream a bit. So everything I showed so far is concrete, but let me dream a bit how I believe, or we believe, that blockchains of the future could be if we power them using pi squared. Programming languages should not be hardwired or predetermined in the programming language, in the blockchain. Okay, you should not have a blockchain on EVM blockchain, on a WASM blockchain, or a Python blockchain, or a Rust blockchain. Programming languages can be data like anything else on the chain. Programming languages are formal semantics, and the formal semantics are publicly available. They will be on chain, publicly available. Now, transactions will have to refer to a particular programming language, actually even version of a particular programming language, because the same program can give you different results depending on different versions of the language. Okay? And now, these programs will be executed once and for all. A proof of proof will be generated, a ZK proof, ultimately, that attests for the correctness of the transaction. And now, the transaction can be settled universally on the blockchain without ever executing the program more than once, and correct by construction. You see, you don't have to trust compilers. You don't have to trust interpreters. You simply verify the mathematical proof. That's it. And with this, I'd like to conclude and maybe take a question or two. We believe that verifiable computing is the future, and we have a unique opportunity to do it right at this point. And by right, we mean to be universal and correct by construction. All right, any question? We have 3 more minutes. Yes? With a mic or yell. What? Go back? More? Can you come closer? Come closer. The support vector machine? It's a very small machine learning model. Nothing deep. It's just a textbook example that. Yes, but it was not our goal. Yes, we can use it for fine-tuning, but it was not our goal. Our goal was simply to generate a ZK proof for an ML inferencer. That was it. How much cost? Cost in the sense of cost of ZK proof generation? Well, as you can see, 28 seconds in the latest version, but horribly initially. All right, 1.5 minutes left. Yes, please.
Thank you. Just really quickly, this is verifiable compute without the possibility of privacy, or can we have privacy as well?
Sorry, can you speak closer?
Does this allow for privacy, or is it just straight up verifiable compute?
So we believe privacy can be done at the level of mathematical proofs. It depends on how you generate the mathematical proof. Okay, for example, if you don't want to reveal your age, but only that it's larger than, you can prove the mathematical property that exists an age such that this happens. And you get that mathematical proof from the execution of the program. But now the way you encode it in the formula and you store it on chain, right? You see, so here, you'll have to, well, I cannot point, but that blue box is a mathematical claim that everybody can see. There's the claim that there exists an age larger than 21 such that. And you get a proof for that, and now that is ZK'd, and you don't see the actual mathematical proof, so you cannot extract the information. That's a very good question. So we believe that's how it should be done. We believe that separation of concerns is golden, right? So we should separate the concerns of mathematical reasoning, as we know it, from the ZK reasoning, and use the ZK to implement verifiers for mathematics. All right, 0 blinking, so I'm done. Thank you.